All right, hello all, and welcome to the first video in my series, Vic Explains Calc 3 Concepts. Okay, so let's get started with the first question. It's going to be, consider the function f of xy equals 5 minus 2x squared minus 2y squared. So part A says, calculate a vector perpendicular to the level curve of f at the point -1, -1. Then draw the level curve contour of f at that point and indicate the direction of the perpendicular vector. This will help you understand the local geometry of the function at a specific point. So right away when I'm seeing this, I'm noticing how it says a vector perpendicular to the level curve. So like I don't want to just find like some random vector and try to like make it perpendicular. Like that's just gonna be way too hard. So like when I see this, I'm immediately thinking of a vector, a gradient vector of a two variable function. And then let me just pull this up right here. Let me see. Yeah, right here. So a gradient vector in the plane is always going to be perpendicular to the contour of f through AB. Right? So like this just lets us know that like the gradient vector is what we're going to want to be looking for. So I'm just going to pull up my work that I did right here to show you guys. Let me see. All right, yeah. So when we're looking for the gradient vector of, I think that's a AB. Yeah, sorry about that, guys. I'm just using pen. I didn't feel like using white or whatever. But yeah, when we're looking for the gradient vector of AB, the formula is going to be equal to the partial derivative with respect to x of AB, the I unit vector plus the partial derivative with respect to y of AB, and then the j unit vector. So, so with this formula in mind, the first step you want to do is just to find the partial derivative with respect to x. And then, so when you take it with respect to x, we can just kind of regard this as a constant, so this just becomes 0. Then we can regard this as a constant, so this becomes 0. And then the derivative of -2x squared is just going to be -4x. And then when we substitute in the values -1 for x and -1 for y, well, we only have x here, so this is going to be equal to 4. And then the same process for the partial derivative with respect to y. We just treat this like a constant and then treat this like a constant. And then this is what we actually take the derivative of because it's with respect to y. So this is going to be -4y. And then once we substitute in the -1 for y, we're going to be left with equals to 4. So now we can plug in these two values into our formula, and we're going to get the gradient vector at the point -1, -1 is going to be equal to 4i plus 4j. And then I think for the next step in the problem, let's see, they wanted us to, so draw the level curve or the contour of f at that point and indicate the direction of the perpendicular vector. Okay, so what I did here, I'm sorry, it might be a little bit hard to see for you guys, but so essentially we have this two variable function right here, f of xy. And then when we have -1 as the x and then -1 as the y. Oh wait, yeah, as the y, we're gonna get, what is that? 5 minus 2x squared, x -1, -1 squared is gonna be 1. So 5 minus 2, that's 3. And then 3 minus, what is that? -1 squared, that's 1. So it's gonna be 3 minus 2. That's gonna give us an output of 1. So just to recap, when we have -1, 1 as the inputs, we get the output of 1. So then that's just what I drew here pretty much. Because when it asks us for the level curve, right, that just means we like whenever I see the word curve, I'm immediately thinking of 2D, right? And then when I see the word level, I'm thinking of like it's gonna be held at a constant. So in this case, we're using the constant one, right? So this is going to be the 2D graph with the output held constant at 1, right? And then it wanted us to indicate the direction of the perpendicular vector. Okay, so then this is the perpendicular vector that we found. It's going to be 4i plus 4j. And then, so since the x component is positive and the y component is positive, right? That's why we're getting it in this direction, right? It's like we go positive in the x direction and then positive in the y direction right here. All right, so now let's move on to part B. So it says, after understanding the local behavior at one point, now draw at least 3 different level curves, contours, of f of xy over a wider range. Clearly label each curve with its corresponding level, i.e. the constant value of f of xy, to explore how the function behaves across the plane. Okay, so essentially they just want us to build off of the contour we drew for part A, but this time they just want us to add on just 3 different level curves, right? So let's see what I did here. Okay. So just sorry for the drawing, by the way, guys. I'm an engineering major, not an art major, like it's the best I could do. But anyways, let's see. So I just kept the same middle one as before, right? It's gonna be whenever you have, like, let's say inputs of 1 for x, 1 for y, or what we did in the last one, input of like -1 for x, -1 for y. We're gonna get the output of 1, right? Sorry if it's a little hard to read, but this is the one right here, the output for this level curve or this contour, right? Uh, okay. So then the next one I did is when we have the inputs of 2 for x and 2 for y. So when we input these values, let's go right here. Should do some quick mental math right here. I'm gonna put the 2 right here for x, that's 2 squared, that's 4. 2 for y right here, 2 squared, that's 4. So what is that? It's gonna be 5 minus what is it? 5 minus 8, that's -3, minus another 8, that's -11, right? So boom, I'll put -11 for this contour or for this level curve. And then I just repeated the process here just 2 more times essentially, right? So when we have the inputs of 3 for x and then 3 for y, and then we plug 3 in for x here, 3 in for y right here, we're gonna get the output of -31. And this is gonna be held constant all around the curve. And then same for here. So when we have the inputs of 4 for x and 4 for y, and we put them back into here, same thing here, guys. We're gonna get the output of -51. So this contour diagram that we've sketched here, it's essentially just kind of giving us an idea of how our 3D graph is gonna look like, but we're just sketching it in 2D, right? So we're seeing how, like, as we get closer to the center, the outputs are increasing. So like if you've seen this function before, you're gonna know this is gonna be that sort of like bowl-shaped, the paraboloid, right? Except it's just facing downwards, right? Okay, that wasn't too bad. Now let's do part C. So part C says, extend your understanding of level curves to 3D by calculating a vector perpendicular to the surface, z equals f of xy, at the point -1, -1, 1. Sketch the surface plot near this point and show the direction of the perpendicular vector. This will help you connect how level curves translate to a 3D surface. Okay, so now let's see what I did here. So first, calculate vector perpendicular surface. Okay, so this right here is going to be the same concept as what we did in part A, right? When I'm seeing the words a vector perpendicular to the surface, I'm immediately thinking of a gradient vector here, right? And then since it's saying surface, right, this word is making me think of right here, yeah, 3D, right? So surface corresponds to 3D, and then curves correspond to 2D, right? So let's see. And then I can even bring this up right here real quick, just so you guys understand. Let's see. Yeah, so this is gonna be the gradient vector of I think it's a three variable function, right? This is gonna be, yeah, so the gradient vector of f of ABC is gonna be perpendicular to the level surface of f at ABC, right? So now let's go back here. Um, okay, so then the issue right here is that we want to find the perpendicular, right? So we have to use gradient vectors. It's gonna be the easiest way for us. But now, since we want to use a gradient vector, we need it to be a three variable function, right? Function of three variables, right? See how right here it's like f of ABC, except right now we're still at two variables here, f of xy. So I'm going to show you what I did here on my work. So I'm using this, let's see, this capital F here, just to symbolize that it's going to be a three variable function, right? So I essentially, yeah, like I just kept the same function as before, right? And then this is going to be equal to z, right? But instead, I just like subtracted the z, moved it over here, and then set this equal to 0, right? You can kind of see this down here, right? So it's still an equivalent equation, right? It's still the same function. It's just now z is going to be one of our inputs, right? It's going to be a three variable function, right? You set it equal to 0. It's still equivalent. So, and then right here too, I just wrote the formula for the gradient vector of a three variable function, like ABC, right? So this is the formula right here. It's gonna be the partial derivative with respect to x, I, plus a partial derivative with respect to y, j, plus a partial derivative with respect to z, k. Ah, that's a mouthful. Okay, so let's see. All right, so the first step I did here is going to be calculate the partial derivative with respect to x. It's going to be very easy here. Let's see, we already did this up here, right? Yeah, so this is going to give us the same values as we got for the first one because it's only x right here, right? Like we're not going to be plugging in this z right here. So the same way we got 4 here, we're going to get 4 here. And the same way we got 4 here, we're also going to get 4 here. Now, the thing that changes here in this gradient vector is going to be the partial derivative with respect to z, right? So when we do that, since we're taking it with respect to z, we just treat this like a constant, this constant, constant, and then we only take the derivative of this part. So it's just going to be -1, right? And then I could have just skipped this step, right? Like we know no matter what you substitute in, like there's no variable to substitute in. So it's just going to be -1, right? Okay, so now with these values that we just found, we can substitute these in to our formula for the gradient vector right here. So the gradient vector at -1, -1, 1 is going to be equal to 4i plus 4j minus k. Okay, and then I think they wanted us to sketch something here, right? If I'm not mistaken. Okay, yeah. So they just wanted us to now just sketch a quick surface plot just so we can kind of see like what the gradient vector is doing here or what the perpendicular vector is doing here. Okay. So what I drew here, I'm very sorry guys, like I'm not too good at drawing, but let's see. So this is gonna be kind of how it looks like, right? It's gonna be the upside down paraboloid, right? And then we know that, let's see. So yeah, so the maximum is gonna be at 5, right? because since it's pointing downwards, we know that there's a maximum at the top. And then that's gonna be essentially when it's like x is 0 and y is 0, it's just gonna come out to just 5, right? So we know that the maximum is gonna be 5 here at the top. And then I just kind of like just eyeballed it, like this is kind of how it's gonna look like. And then if you zoom in real closely here, you can see I was trying to draw this vector. It's just very hard to draw in 3D. But essentially, it's just gonna be pointing like inside of the paraboloid, right? Like we have the, let's say the paraboloid right here, and then it's like it's perpendicular to this. So it's gonna be like going inside. Oh, this is very hard to explain. But like it's just going inside of it, essentially. It's like what I'm trying to say. And then this is gonna be the x component of the vector, the y component, and then the z component, right? And then it's gonna be the vector is gonna start at the point -1, -1, 1, right? Okay. Hopefully you guys understood that. So now we have part D, which says to see how the entire surface behaves, sketch the full 3D surface, z equals f of xy, and highlight how the level curves from part B correspond to the surface at different heights. This connects the 2D contours to the 3D surface geometry. Okay, so this essentially is just saying like it just wants us to sketch the full 3D surface just so we can see how the 2D and the 3D connects, right? Essentially what it's saying. So this drawing I'm actually a little more proud of. Like it's not the best, but like I did a bit better on this one. So let's see what I got going on over here. So it's the same like sh general shape as before, except here I just drew in the what is it called, the contours, right? Is that what they're calling it? Uh, yeah, yeah, the level curves is what they're calling it. But it's the same thing. So if we go back to part B, we can kind of see how like this is essentially like the top-down view, right? If you were to get the three axes and you were to look at them from the top, from the z-axis, this is the view you would get, right? And then I kind of just translated that over here, right? So it's gonna be an output of 1 at the points like let's say like 1, 1 or -1, 1 or -1, -1. Right, it's not really perfectly drawn to scale, but you can kind of see, right? And then pretty much as we're moving farther away, we're just getting more and more negative, right? Which is what we got going on here. Like as we're moving farther away, we have -11, then -31, and then finally -51, which was the last one I drew over here. Okay, so now let's go to part E. So part E says, consider the gradient vector of f at -1, -1. What is its relation to a vector tangent to the path at the point -1, -1, 1 that points uphill? This will help you connect the gradient's direction to the concept of ascent on the surface. All right. So essentially what I wrote here is just that, so the point -1, -1, 1 is just going to be standing directly above the point -1, -1, right? Like, let's see if I kind of drew it here. It's hard to see. Yeah, so like, so here is let me see. Yeah, the gradient vector f of -1, -1. This is the gradient vector of -1, -1, right? It's just going to be pointing straight to the center. And the center is where there's like the greatest rate of increase of f, right? And then this this vector as tangent to the path and points uphill, it's gonna be following the same path. except now we just have like a z component in this vector, but it's following the same x and y components, right? So we just know that this vector, and let's see what else I wrote. Since the vector gradient vector of -1, -1 lies in two space, pointing in the direction in which f increases the most, which is going to be uphill, it must lie directly below the vector tangent to the path at the point -1, -1, 1. All right, so that's pretty much what it is. And finally, we have part F. So part F is saying, at the point -1, -1, 1, on the surface, f of xy equals 5 minus 2x squared minus 2y squared. Calculate a vector n vector perpendicular to the surface and a vector t tangent to the curve of steepest ascent. And it just says, understanding these vectors will help you explore the steepest ascent, directions, and perpendicularity in both 2D and 3D contexts. Okay. So what I did here, all right. So first we have the n vector, right? Perpendicular to the surface. So as we already know from part A, like when we're hearing or from part A and part C, right? Whenever we hear this perpendicular to the surface, we're just thinking of gradient vectors. And we already solved for this in part C, right? So we don't have to do the same work again. So I kind of just copied and pasted the gradient vector at -1, -1, 1. It's going to be 4i plus 4j minus k. So I just kind of copied that and pasted it over here. So now the real issue here is going to be finding the t vector, right? We want it to be tangent to the curve of steepest ascent. So what we know here is that, like, as we know from the as we know from the previous part E, we know that it's gonna have the same x and y components, right? It's following the same path. It's just that for the gradient vector, it's perpendicular and it's like pointing inwards of the graph. Except for the t vector, we want it to be tangent to the curve. So if the curve is like this, we want it to be tangent and going on the steepest ascent. So while n is perpendicular going inside, we want something that's tangent and going up. So we know that it's gonna be equal to 4i plus 4j, the same as the n vector just perpendicular, which is the gradient vector. We just don't know what the z component is gonna be. That's why I just used just a variable a as like something we need to find. Now we do know though that a is gonna be a positive integer, right? Because we want to be going like uphill, right? Ascent, right? Ascent going up. So the a is definitely gonna be a positive value. And then so let's see. So what we're gonna do here in order to find a is we're gonna realize that these two vectors are gonna be perpendicular, right? Because while the n vector is perpendicular to the surface, right? The t vector is tangent to the surface, right? So as the n vector is going perpendicular in, we have the t vector, which is perpendicular, going tangent. Hopefully that makes sense, guys. So, okay. So we want them to be perpendicular, and we know that when we take the cross product of two vectors, if they're perpendicular, they're always going to equal 0. So that's just what we did. We're just taking the cross product, or oh, no, I'm sorry. We're taking the dot product. Yeah. So whenever dot product of two vectors is 0, it's because they're perpendicular, right? Okay. So we're just doing that here, right? We set it equal to 0. And then when we're taking the dot product, we're just multiplying the x and x components and then adding it to the multiplying the y and y components, then adding multiplication of the z components, right? It's nothing too difficult here. So we're gonna be doing 4 times 4 plus multiplying the y components, again, 4 times 4 plus multiplying the z components. So -1 times a. And then once we just simplify here, we're left with 32 minus a equals 0. Get a to the other side, and boom, we got a equals 32. So with that, we can plug this a value here into our t vector that we're just missing the z component. And that'll leave us with our final answer of the t vector equals 4i plus 4j plus 32k. All right, guys, that about sums up today's lesson here for you, covering gradient vectors and then 2D and 3D space and level curves and level surfaces. Let me know in the comments down below if you have any questions, and thanks for watching. I'll see you guys next time.